geography. So it is fun to see what you are all up to here, and looking forward to learning more about your department, labs, and everything. So I have kind of 3 talks in one, but they are all linked by turbulence. I know we have a variety of backgrounds of people in the room. And so I am going to bring us all to the beach to kind of get everyone on the same page for how we want to think about the problems we're going to discuss today. There's also a few natural kind of break points during this, so we don't have to wait till the end, but I'll try to point those out. But if you want to jump in, go for it. All right, so if we think about being sort of offshore in coastal nearshore zone, as we have waves that approach the beach, they will begin to steepen, and at some point you are going to have some sort of wave breakage, whether you have spilling, plunging. There's different types of wave breaking, but all we're concerned with right now is that there is going to be some injection of momentum that penetrates downwards through our free surface. That jet, or that momentum transfer, is going to start to create eddies, start to create turbulence and chaos in the water column. And although the tip of the wave, that might not hit the sand bed beneath, but these turbulent eddies, these are then stirring also the water around it. So this turbulence is able to propagate all the way towards the bed. With that, we are going to have these local, instantaneous interactions with our sand bed. And so that can start to generate local stresses that suspend the sediment or create little, local mixing processes at our bed that were caused by some superficial injection of momentum. All right, now recall, this wave is still propagating on shore. As the wave is carried on shore, the turbulence propagates with it. And with it, that continued sediment suspension continues to occur. So now we approach what's called our swash zone. So this is the region of the beach that's continuously uncovered and covered by instantaneous wave runoff. This is, where I used to build drip castles in the sand as a little kid, trying to get right to where the water ended, but not get washed out by the next big wave. So our swash zone is really, it's not a normal turbulent boundary layer. It is a very fast gets turbulent boundary layer. There's obviously turbulence, there's shear stress, but we're carrying all of this kind of extra offshore generated turbulence with us. So all of the shear stress that we see at the bed wasn't just created by that mean velocity, it was already there, and then it can get enhanced during that uprush process. And so with all of this extra turbulence, we're seeing way more sediment transport and suspension than we would have seen if this were just, just water running up and down that didn't have that offshore wave breaking source of the turbulence. All right. So as our flow continues to run up our swash zone, ultimately the water slows down, sediment loses its inertia, begins to fall out of suspension, and we will ultimately have a nearly clear water for a very brief moment up at the top of that swash zone. This is also when my mom was giving us lunch at the beach, she would say, go wash your hands in the ocean, which was probably really dirty. We probably should have eaten as we were. But I remember waiting for the water to come up. I waited for the sand to fall, and then I splashed my hands really quick because the water looked clean. I had no idea I was going to get my PhD in this, 30 or 20 years later. So anyway, so now we have our water, needs to retreat back to the ocean. We have this clear return flow. This is our normal, turbulent boundary layer. Shear stress at the bed, some of that sand that was just deposited is going to get washed back down shore just through normal friction generated by stress. All right, so what we have here, what we're interested in, we had this shear-driven turbulent boundary layer, but with suspension at the bed. But what I'm really interested in is, what if we take away any of the shear and we just say, what would the turbulence have done? That offshore wave-generated turbulence, how much sediment suspension is that responsible for when there's no oscillatory flow, no mean shear, no uprush, no backwash, none of it, just the turbulence? Because we know that instantaneously we see a ton of sediment suspension, but the theory tells us we shouldn't. So we go back to, hopefully everyone's had an introduction fluid mechanics class. If not, you're getting it today. So normal turbulent boundary layer, fast velocity away from our wall, goes down to 0 at the bed, no slip, boundary condition. Whatever our velocity gradient is at that bed tells us what is our shear stress going to be, our mean, time average shear stress. If we go into the sediment transport world, we have our Shields curve here. So what this tells us, we have our particle parameter on the horizontal axis. So what is the median grain size? What is the relative weight of our particle to the water, to our fluid, et cetera? So stuff about the particle on our vertical axis, critical mobility parameter. Effectively, what's our non-dimensionalized shear stress? Do we have enough mean shear stress to mobilize a piece of gravel or a grain of sand? If we're above this curve, we have mobilization. If we're below it, the sand and gravel stay put. This is all based on having a mean shear stress, on having, that uprush, having that velocity. And so this really works very nicely. This is a picture of Taganic Falls in Ithaca, where I was for grad school at Cornell. And so if we have some sort of uniform flow, our water, is in a small channel before it comes over the waterfall. On a normal day, it's nice and clear. Then we have a lot of rainfall. It's increasing the velocity. Yes, there's also runoff and other processes happening here. But we know if we exceed that mean shear stress, we're also picking up the sediments and silts and whatever were just sitting peacefully in the channel before. When we put more stress on them, they get picked up. So this works really nicely, the whole shields idea with mean shear stress for certain types of flows. What if we think about, flows generated by mussels, which are bivalve filter feeders? They're constantly cycling water in and out through orifices. And if you take a really dirty fish tank and put a bunch of mussels in, they can clarify this in about 30 minutes. And so obviously there's no mean flow in here, it's a fish tank, but you have all of these local, inward and outward jets happening down here. So this thing is getting stirred up. These are the types of flows we do not know how to characterize and how to predict what the type of transport is, if there's going to be sediment suspension, sometimes even what the settling looks like. And so to go back to the beach, I'm just interested in this because I love the beach. I get to study this now and get excuses to go on vacation and get paid for it sometimes. And so I want to know, what is pulling up all of this sand? What is pulling up all of the sand over here? If we can just isolate this down to a super turbulent case, how can we characterize it and kind of, for sediment transport applications, reframe the Shields diagram to say how much instantaneous turbulence does it take to suspend sediment. But then today we're also going to look at this in a couple of different applications. So I'm a lab person. The turbulence facility we used to do this was originally developed by Evan Veriano, who's a professor at Berkeley. I have since taken his tank and made a few modifications to it. But this is the world of these jet stirred tanks. So we have a water tank. The new one we have 84 centimeters wide, 1 meter high, nice square box. On the top of this is a randomly actuated synthetic jet array. All right, these are synthetic jets because they're injecting momentum, but not mass into the flow. They're just little recirculating bilge pumps. All right, they are randomly actuated. So as these turn on and off, they will generate turbulence in their wakes. These wakes then interact with adjacent wakes that are also turning on and off. And ultimately this merges into a layer of nearly homogeneous isotropic turbulence. So just perfectly well stirred. Homogeneous, same everywhere, isotropic, equal in all different component directions. So if you are in this part of the flow, you have no idea which way is up or down. You no longer feel the jets either. They're just kind of dancing around on the top of the tank. And then we form this layer of isotropic turbulence that then is going to interact with our boundary, starts to break down in isotropy. So we're going to show different cases of different bed conditions down here and see what types of phenomena we get. We'll also have a little bit of a restructuring of the turbulence at this lower region. Obviously, we said, we have a breakdown of isotropy, so our eddies kind of might get deformed. We have different phenomena happening. And so this is the boundary layer we want to look at, is a zero mean shear turbulent boundary layer, all right? Quick little video to kind of how this works. This tank has 256 jets. It's a lot of wires. And so each jet is individually turning on and off on these different algorithms that we have to control the turbulence. And you can see it starts to look like a jet, but then kind of gets washed up with what's around it. This video, things did not go quite so well. And you can see this jet is penetrating deeply enough to be of concern. So we don't really want the jets to make it quite that far down because they might actually hit the bed and then we don't have a zero mean shear condition anymore. But we play with the tuning of the voltage, the average amount of time the jets are on for, how many jets are on, all this stuff to get the turbulence we want. Here is just a scale of the tank. All of the students kind of have to get it at some point to clean it. So these were my first graduate students. That was me during my PhD. up in the top. And then this is the tank we've built a little bit bigger at UT to do more stuff with. All right, so where we are. So we're going to basically, use the idea of that tank to discuss 3 different problems today. First one, mixing across a density interface, so stratified flows. Second one is going to be the sediment suspension and bed morphology case that we sort of introduced in the near shore. And then the third, we're going to look at how we can use turbulence to melt ice, which was something I was not thinking about at all in grad school, but here we are. And then I'll give you a quick look at the flumes and just kind of what my life is like at UT. So, all right, any quick questions yet? I'm gonna keep going. Oh, no, we got it. Okay.
So the dirt in the water will go into the muscle.
What's that?
So the dirt in the
Yeah.
water. Okay.
Yeah.
Gotcha.
Okay. So yeah, I think that's, I mean, I don't know much about muscles, but that's somehow.
That's okay. I don't.
Somehow where they're getting stuck. All right, but you let me sneak in some water. All right, so first, mixing across a density interface. All right, so close to here, I think this is the first time I've given this talk in Texas. So you guys might actually know these places, but off of Oso Bay, which is adjacent to Corpus Christi Bay, there is a power plant or a desalination plant that brings in water from the Gulf, desalinates it, uses the clear water to cool the industrial facilities adjacent, but then they're left with this really salty brine that they need to discharge back and pretend it never happened. Texas does not have the most stringent of environmental regulations, and so what I'm told is that they use California's. However, the Gulf of Mexico and Pacific Ocean, not quite the same from an energetics standpoint, nor a bathymetry, topography standpoint. And so my colleague, Ben Hodges, about 10 years ago, did some studies, did some measurements along a transect where Oso Bay enters into Corpus Christi Bay to see if these desalination brines were really mixing out or not. And what he found was that we have really strong gradients of temperature, salinity, and dissolved oxygen. And so basically they're not mixing, short answer. But what we do see is that his model was that when they are discharged, initially there is a slope. We have a gravity current going down slope. It is going to be able to entrain a lot of the ambient water, drop a little bit in concentration as it begins to spread out. But what happens next is we reach a region of really not interesting bathymetry. This flattens out, the current loses momentum. There is nothing else to drive continued entrainment that we need to continue to dilute this plume. And so instead what we see is this region of hypoxia, where we have basically the salinity is so high that it consumes all of the oxygen. And this can lead to ecological issues and dead zones, of which there are plenty in the Gulf. And so what I wanted to see was, if we're in this region, we no longer have mean shear, right? We've lost all of our velocity, all of our momentum. But we're in the Gulf of Mexico or in the Bay or wherever. There's a lot of wave-driven turbulence. There are passing ships, there are tides, there are sources of flow that might be generating ambient turbulence in the water above this. And so if we understand what is the ambient turbulence, can we start to understand whether there is going to be enough, sorry, this thing is very sensitive today. Technology is not so good for me right now. If we understand, the salinity gradients, differences in molecular diffusivity, the turbulence intensity of the above flow, basically what are the conditions that are going to foster conditions where this dense layer totally mixes out and we pretend it never existed and life is good, or possibly it might even be compressing it or eroding it or doing different things. So by messing with the flow and kind of our geometric or material constraints, we want to see how we can characterize mixing and entrainment and ultimately, try to avoid issues like this in the future. So we use our turbulence tank, same setup that you just saw. Here we have a dense layer. What we are using for this currently is sugar water. That's because sugar is easier to deal with in the lab than salt, because it doesn't corrode stuff. It just makes them sticky, but we can deal with it. It is also pink for reasons you will see in a moment. I will say that sugar and salt also have different molecular diffusivity. So we plan to do both. We want to get all the kinks worked out with the sugar first before we start corroding our jets. So to make measurements, we're focused kind of in this region. So we use particle image velocimetry, PIV. So this tells us what's happening in the fluid velocity field. We can definitely do this in our water layer. We can also sometimes do this in our sugar water layer, but sometimes we're having issues with this. But we have neutrally buoyant particles dispersed all through the fluids. They get illuminated by a laser. We take photos rapidly of them, and we track how all of the particles move in time to calculate the two-dimensional velocity field. You can also use multiple cameras to get all three components of velocity in a plane that cuts through the density interface. We also use laser-induced fluorescence, LIF. And so we said that that sugar water layer is pink. It is pink because it is dyed with rhodamine B, which is a fluorescent compound. This acts as a passive tracer to let us quantify mass, essentially. So as, again, the same laser, these measurements happen simultaneously, just different cameras with different filters to let them see the different frequencies of either the reflected, green particles versus the fluoresced dye, which is at a different frequency or wavelength. This lets us quantify the mass as we actually have mixing events as the turbulence interacts with that density. So we get 2D slice of mass concentration, 2D slice of velocity. One of the issues we have run into with this is with regard to index matching. And so as we have different density fluids, we also have different index match, or each fluid has a different index of refraction. And so as the light goes through our fresh water, fine, but then it hits that sugar water interface and it doesn't just continue straight through, it's going to bend. All right, and so if that means that our laser light sheet bends out of plane, we no longer have this nice consistent light sheet that our camera is focused on. We get blurry, horrendous images that we can't do anything with. And so instead, we know we want our sugar water in the bottom. And so what we do to our top layer, instead of using fresh water, we mix isopropyl alcohol. So like alcohol you buy at the drugstore to clean a cut or whatever, which is painful, but you got it. Put alcohol into our water to change the index of refraction. So we still have two different density fluids, different viscosities, different molecular dynamics, but the same index of refraction. So our light sheet is able to stay linear as it goes through it. This was a big thing to figure out, but you'll just get to see one slide of it. I'm going to skip this slide, but basically this just shows how we do all these things simultaneously. All right, I'm going to show you a video of what this looks like. You can ignore the caution because I'm going to switch videos, but basically what you're going to see, we have the turbulence above it, and this is our dense layer down here. So I'm going to see if I can get out of PowerPoint real quick. So this is our actual LIF data. So this is the concentration data. I will just say, forgive the streaks. We were figuring things out. It's better now, but I don't have the nice data to show you. So the streaks are nothing physical as far as we're concerned, but this will play in relatively real time. So we have the turbulence on, and obviously we get to see deformations of the interface, moments where these really nice little wisps of fluid are pulled upwards into our water column, penetration of the bed where big, turbulent events will push in. We have some conglomeration of eddies passing through. Overall, our interface for this case, this was, I think, a pretty high density difference, maybe 5% difference between our two layers, which is significant. So our average interface position stays at relatively the same position overall. Obviously, it's oscillating up and down, but we don't just have a rapid whoosh of our dense layer coming up into the top, which we do for our some of our lower density cases. So this is basically the type of data we get. And then what we're doing with this is trying to identify things like internal waves and looking at all of our stable and unstable stratification dynamics to see how we can quantify entrainment or erosion, where we have just kind of turbulence peeling away at this dense layer, as opposed to the bottom layer being able to kind of entrain the top layer and become more dilute. So a couple different competing things happening here.
This is all just driven by the homogeneous turbulence that you got in the box.
Yeah.
And are the because it seems like there's, would you call those waves?
Yeah, there's definitely some large scale oscillations and then smaller scale waves on top of them.
So that's got to be correlated to the size of the box, right? And like, do you know if it's resonant or if it's some sort of you know, mode of the box size or something that allows that to happen?
Yeah, so very good question. I would say at this moment, I would actually say no. Its short answer is yeah, not necessarily correlated with the size of the box or spacing of the jets. Like we're able to, so the tank is 84 centimeters wide, our integral length scale, so kind of our size of the eddies in the flow ranges from 5 to 10 centimeters. And we're able to control the integral length scale by just changing the amount of time that the jets are on for. So it's not even a function of like the jet spacing or any of the geometry, but of this again, answer of like the turbulence activity. These jets are very powerful, and the algorithm is so dynamic that it tends to kind of wipe out anything else that you would have seen from the imposed geometry, I would say. And so, all right, does that answer your question?
Yeah, that does.
But yeah, I mean, it is things we're looking at more in like, especially how do we characterize all of the wave forms, like the large scale and the small scale. And like doing, you know, tracking the boundaries, like what's the boundary in that when you have these, you know, infinitesimally small gradations in the concentration and whatnot. So, all right. Oh, that was supposed to be black. There. So I'm gonna, what time are we? Okay, I'm gonna skip this in the interest of time. But basically, yeah, we end up characterizing a turbulent diffusivity. So if we have high concentration, low concentration, with originally a planar interface between them. If we turn on turbulence, so without turbulence, we have diffusion of particles across that interface because of molecular dynamics. If we turn on turbulence, what we're really doing is just deforming the interface. And so by deforming that interface, you guys saw all of this little nooks and crannies. We now have a lot more particles that are adjacent to the interface. So they're still taking advantage of molecular diffusion to cross over that boundary, but the turbulence is allowing the molecular diffusivity to happen more quickly. So kind of that's how I'd like to think of what turbulent diffusivity means. It's an enhancement still of the molecular process, but by these physical deformations. And so we would love to be able to, you know, kind of use our LIF, that concentration field data, to get through this. However, we have a vertical slice, and so we don't really have an interface, you know, dynamic like in 3D. We have a line, and something that's happening just out of plane may not, like, you know, it may show up in the plane that we're measuring via, you know, some little artifact that makes its way through because it's a very three-dimensional flow, but we're not really sure yet if we can convert a 3D process into, you know, use it in a 2D data set. And so figuring out just how to study this and how to quantify this is a challenge. I'm going to go through this because I want to show you different things. Okay, but I'd rather show you this. So these are some of the physics of what we're seeing. Sometimes in the early stages of running the turbulence, we get these awesome vortex rings that plunge right through that density interface. And really, we can think of the turbulence kind of as just a culmination of vortex rings, but sometimes going in different directions as well. So when we can see like a single nice one really clearly, that's really exciting to see how deep does it penetrate. What is the length scale of that vortex ring relative to the internal length scale of the turbulence? You know, relative to our, like, how do we link our fluid and sediment or fluid and stratified dynamics? We will also then try to link them with sediment dynamics that we see in the next little set. So really interested in our physical length scales, looking at the waves and how these waves can change the interfacial area via all these, you know, large and small eddies that are feeding off of one another, identifying moments where we have like an actual entrainment event, or this would, I guess, be an erosion event, where we're taking fluid from our bottom layer and slowly detaching it until it actually becomes detached. And so we haven't changed the density of this layer. We've changed the density mildly of the upper layer, but, you know, looking at, you know, whether we have basically upper layer, low density water going into the bottom, high density water going into the top, and finding all of these structures in nice little, you know, Kelvin-Helmholtz billows, these wonderful little very uniform waves that we can pull out of here. And so just kind of, we're at the stage of identifying instabilities, I would say, and then ultimately putting this together. So I would say we are at the stage where we have kind of proof of concept experiments showing that this will work. Kind of the complicated things have been getting rid of the streaks Or if we have our laser sheet coming in from the side, if there's a suspension event or an entrainment event happening between where the laser is and where we're actually measuring, it knocks out our light. And so it makes it look like the concentration dropped, but really it's just we blocked our light. So we've been doing all sorts of gymnastics with our lasers, our cameras, to try to get really nice, perfect data sets to measure what we want to measure. We see a lot more, obviously dynamics at the interface, right at the interface. The turbulence sometimes penetrates really deeply, but not usually, especially if we have a high density gradient. So this is what we're just trying to figure out, kind of where is the entrainment potential the greatest? Under what conditions do we see either entrainment or erosion, or really nothing at all, or maybe really just standing waves? And so ultimately, I would like to, kind of take this back to the original case of, which was a discharge plume, where we have both mean shear and turbulence. So right now we're digging into the turbulence probably for a couple of years, but then I'd like to take this back and have plumes entering ambient turbulence. And so we can sort of build up the field conditions strategically in the lab. So I think, yeah, this is where, if you want to ask any other questions about the density stuff, I'm happy to take one or two quick ones. And there should be no more technical issues. For the rest, this just carries out. That's normal.
I have a bunch of questions, but I don't want to take up all the time. So I think I want to let you.
All right, we'll keep going and you can come back at the end. Thank you. All right, next, similar situation, but we're going into sediment suspension. Okay, back to the beach, back to the near shore. Same tank, taking out the sugar water. We have sand in the bottom. This is what my PhD spent a lot of time on. What was meant to be a 2-year master's project turned into 8 years of grad school, and now probably multiple PhDs for multiple of my students, of things that were a lot more complicated than my advisor had ever anticipated. So we have sand in the bottom, nothing too special about it. And we're trying to identify again, what are, we have no mean shear, but we do have suspension. How do we characterize the extremes of the turbulent energy that pull our sand up into the water column? All right, so back to the beach again. We're thinking about using this turbulence chamber as a model of wave breaking generated turbulence. And when we have turbulence that's much greater than what we would have seen from the mean shear, how does it suspend stuff? So first, we can quickly characterize, this is the turbulent flow in the tank. If we do PIV above the bed, we have our URMS, this is our magnitude of our fluctuating velocities in the horizontal direction parallel to our bed, and W is our vertical velocity fluctuation. So as our fluid is approaching the bed, it can penetrate a little bit because it is porous, but we're going to have a big intercomponent energy transfer from vertical to horizontal. So this is our kinematic boundary condition, or our intercomponent energy transfer. So loss of energy in the vertical that becomes really strong energy in the horizontal. The way this shows up in sediment is through these splats. So a splat is a real scientific word, but it is that intercomponent energy transfer. And it's kind of these structures where you'll see this radial burst of sand traveling laterally outward from some point. I've got a few more views of these. And so this is our intercomponent energy transport. What I was saying before, if you remember in the stratified, where we have those vortex rings coming through, thinking about the length scales of those vortex rings, how do they compare to the length scales of these splats that we see on the free surface? These are some of the things we want to pull together, because the sand and our density are different, are obviously going to act really differently, but how can we think about the scaling between those different materials? What we also have is other suspension structures. So this is kind of our image of the splat, where we just have this really low radial burst of sand. But these are vertical PIV images. So they're not the best for characterizing a splat that happens really flat. But what PIV does get nice is these bed attached vortices that will spin like little tornadoes around the tank. Or if you have two splats adjacent to one another, they can create an anti-splat when you have this nice ejection of sediment coming up because of the collision of those two splats against each other. So we can get some really neat suspension data happening. So we're happy to see that the turbulence still suspends sand with no mean shear. But then how do we characterize that turbulence stress? So recall, if typically we think of wall stress in terms of the mean velocity gradient, but our mean velocity gradient is 0, that doesn't do much good. if we think to turbulence class, which I know some of you have had, we can think of our total stress as a sum of the viscous shear stress here, which is our the curve that, or which curve, no, the bottom going up. So at the wall, we have our stress is completely dominated by this viscous stress. However, away from the wall, we instead can think of the Reynolds stress. So this is the product of those velocity fluctuations in the horizontal and vertical directions. However, if we average that over all time, that's going to be 0. We're homogeneous, we're isotropic. So basically all of my statistics average out to 0, which is really frustrating. And so even though a lot of people can say, well, I can't measure the viscous stress, but I can measure the Reynolds stress. And if I have the magnitude of the Reynolds stress, I can approximate it as our magnitude of our viscous stress, and life goes on. I can't do that. What I have, though, is I can look at histograms of the products of the velocity fluctuations. Again, centered on 0, not super interesting, but way out in the tails, we have very high magnitude velocity fluctuations. High magnitude in a civil engineering perspective, not high magnitude for many of y'all. But what we see is if we compare this back to the Shields curve that remember told us basically what's the critical shear stress you have to exceed in order to suspend sand or gravel or material at different particle sizes. We have centered just about close to 0, but as we get out into the wider percentiles of this, we're getting to pretty high velocities. Shields tells us that if we had an equivalent mean shear of 1.3 centimeters per second, that we should see suspension of this sand or see motion of this sand. We exceed that, and in our 25% max and 25% minimum tails. And so what we're looking at is basically how can we put this into something to say whether we expect to see suspension. What we also see separate from the suspension is this. This is a very old video of mine from 2009. Time-lapse images, these are taken every 1 minute apart. It will speed up at 4 hours. At the 4-hour mark, it speeds up, and the images are every 10 minutes. So it's going to look like it gets a lot faster, but it's just I was having battery issues. And so what you can see by now, there are these wonderful ripples forming. There are ripples that are attached to the walls. That is due to even though we have a ton of turbulence, there is a very weak mean recirculation that drives a little bit of structure adjacent to the walls. But we know that the turbulence is not homogeneous when you're within 2 integral length scales of our wall. And that is the length to what's like 6 hours in by now. Or that's 12, I guess. I'll replay it. So long way to say you can ignore what's happening at the walls because that is not where the turbulence is actually homogeneous. I've been asked many times, do you only have ripples because you have walls? But we sort of have ways that we can manipulate the jets to essentially turn the walls off, which is really a question a little bit from before. We're really interested, or I'm really interested in what's happening in the central core, though, where we have near isotropy, near homogeneity. These ripples will just kind of continue to merge and dance around and migrate for as long as I leave the jets on. But you'll see it. Sometimes we have little 3-sided cells, sometimes they're 4 or 5 or 6. These are all adjacent to one another, kind of packed into these little patterns. I'm not sure if anyone's familiar with star dunes, but we've thought about that a little bit in this context of thinking about, star dunes are kind of like, so you have even or odd numbers of arms coming off. It can tell you something about the directionality of the shear stress because ours are sort of going in all directions, kind of reinforces this concept of the isotropic turbulence. So we see these ripples. I have no idea where these things come from, and it drives me totally nuts. Okay, we had sand ripples. I don't know where they came from. We have suspension, but we also see ripples forming without visible migration of particles. So let's go to our turbulent kinetic energy balance. There are a lot of terms missing from this that you may have seen in your coursework or in research. The ones that are already missing are missing because we have 0 mean flow. And so we don't have, advection, and we don't have a lot of other parameters that normally you would have in a TK balance. I've just kept the most energetic and ones that I think are the most interesting, but the ones that we might actually be able to measure something, not just because I thought they were cool. So starting from right to left, we have dissipation, all right? Dissipation of our turbulent kinetic energy into heat at our viscous scales. We can measure this directly using PIV. Having to chat about it, but I'm not going to on this one. So we're non-dimensionalizing everything by dissipation. So relatively uniform dissipation throughout our turbulent flow, even as we get into the boundary layer, but then an increase in the magnitude as we approach the bed, all right, where those viscous processes are really happening. All right, then normally dissipation at the bed, the magnitude would be balanced by our viscous diffusion term, but that is one of the ones I didn't even include on here because it's going to be 0 in this type of flow. I did measure it, it was 0. So this is on the left is a normal channel flow turbulent boundary layer. And we really, already at step 1, we can't really directly compare. I don't have anything that's balancing dissipation at the bed. All right, so let's look at production of turbulent kinetic energy. Production is our product of our Reynolds stress. So again, our correlation of our energy or our velocity fluctuations, product of Reynolds stress with our mean velocity gradients. We already said Reynolds stress is 0. We already said we have no mean velocity gradients. So production isn't giving me a lot of hope. If I measure it, it's just about 0. All right, not super exciting. In a turbulent boundary layer, production and dissipation would be in balance with one another away from the bed. But again, I don't have that balance here. All right, turbulent transport, our triple correlation of velocity fluctuations. These are my green elements here. They're a little bit higher magnitude, if I didn't label it on the left-hand side, a little bit higher magnitude in this flow than in a normal boundary layer because we have a whole lot more turbulence and generation of these fluctuations. But the last term that I wasn't really able to delete was this pressure diffusion or pressure transport term, which I don't have a way to directly measure that, all right, unless I had pressure sensors kind of in the flow, which would defeat the purpose of having a nice clear water turbulent flow. So what I can do, because we know that everything else has gone away to 0, what we've done here is say, let's estimate the magnitude, at least, of the pressure diffusion term as the residual of the other terms that I am able to directly measure in this facility. Maybe it is pressure that is balancing out my magnitude of dissipation. I don't really know, but it's the only thing that's left basically at this point. So can pressure fluctuations or pressure gradients generate sediment transport becomes our question. And so these are experiments done by colleagues of mine, but I was not directly involved, where there was an oscillating plate and they said that they were generating pressure waves in the tank via the oscillating plate. And indeed, I know this is really dark, but we saw what was flat merge up into this heap of particles. This will reset so you can see the contrast in a moment. But they were saying that, yeah, this is all pressure induced. I don't think they had pressure sensors in this experiment either, but you can see it, that this pretty quick. This is not in real time, it's accelerated. But they think there's a few studies that have either experimental or field data where we're looking at this pressure induced sediment transport. So maybe that is possible. So that's one of our goals, is to kind of see, we see the sediment getting picked up in instantaneous, super high energy turbulence. We've seen the ripples evolve. We can control the turbulence, like the turbulence levels with that jet algorithm. With that, we can change the integral length scale of our eddies in the flow. We can change the physical makeup of that turbulence. We know that the ripple spacing and the integral length scale are linked. That was something I didn't talk about, but we got it. But where do these ripples come from? Is it possible that we're having localized, bed fluidization or something else happening because of pressure gradients within the bed? And so I'll go through this quickly because I'm just going to show you this setup. So the experiment, we've continued with this. Again, PIV, sand, you'll see we have 2 different layers or different colored sands that we want to start to study, because I've already done a lot of the water stuff above the sand, but we'd like to know what's happening within the sand bed. And so by using layers of different colored sands that have almost identical grain size distributions, we're able to visualize what's happening. And so we run these same turbulence tests that we just saw in like the ripple test PIV that you just got to see. Down here is this little hollow aluminum wedge, about yay big on the camera, people. And we fill this with liquid nitrogen. It makes this awesome plume in the lab, which is really cold and really fun to play with as long as no one gets frostbite. But we fill up this aluminum wedge with liquid nitrogen. They're really cold. Then after we've run a test, we want to see if there was any mixing of the sand grains that are submerged within the tank, indicating that there was possible fluidization or mobilization of grains within the bed due to the turbulence above, and specifically if we have, pressure and velocity are linked Bernoulli. And so as we have turbulence, we have pressure gradients. If that is allowing this bed to kind of relax a little bit during the course of the turbulent forcing, we want to see if we have evidence of it. So this is what a freeze core looks like. The wow moment when it comes out and the sand has frozen onto it because it is so cold. And so we do this at different times during our testing, and then we take photos of the core. So this is a little bit, I guess, less invasive than a more traditional coring technique. We can then identify every single sand grain using just ImageJ and MATLAB. So we can go through and identify the red sand that stayed in the red layer, the blue sand that stayed in the blue layer, and then anything that crossed over. So we can start to kind of quantify how much mixing occurred. But also there's, as you can imagine, a fair degree of error in this. And if you don't go in perfectly vertical, or you bump it while you're doing it and it kind of catches other sand grains, sometimes it can look like you have more mixing than you do. So we are still in somewhat early stages of this, I admit. And so we have a lot of work coming up to kind of keep doing this. But just wanted for you guys to get to see the goals of some of this. This is also linked with a CERTIP grant, which is the DoD's like environmental response program. And so there are munitions, unexploded munitions left over from the prior like world wars and conflicts all over the coasts of most of the world, but mostly, US and Europe, but they're everywhere. They're starting to now become health risks of either washing on shore and they're still explosive, or leaching chemicals, which are bad for the ecosystems there. And so we're trying to use work like this to predict whether munitions that are already buried are going to stay there, or are they going to come on shore? Where are they going to continue to migrate? Can we come up with clever ways to identify and recover them if we are worried about them becoming a health risk? So this is kind of where this work is going with the Department of Defense and DOE a little bit. So this is our sediment work. I think I'm going to go ahead and jump to our last one, and then we'll just save questions for the end because we've already had a few interruptions. So the last bit, I will say this is what's the most fun to me, just because it's the most out of my element. So I'm learning the most. Now we're going to go to fjord. All right, we've traveled a lot today. Ice, very idealized case, vertical ice wall, cold Arctic water on top of warm Atlantic water. Usually we think of warm on top of cold if we're going to have a stable density interface, low density on top of high density. Atlantic water is much, much, much saltier, right, than our Arctic water. And so it is still a stable density stratification, low density on top of high density. But in addition to the thermal gradient, we also have a salinity gradient that lets this stay put. All right, very fundamental, or very, very cartoon idealized situation. Glaciers can melt through these channels that form through the ice. As they do so, it can build up a lot of pressure at the base, and then it's going to eject a freshwater or meltwater plume up back into the fjord. This might be freshwater. It might also pick up sediment. So you may have a sediment-laden plume or just a really nice clear water plume. All right, this is rising up the face of the glacier. You can imagine this may also induce some melting along the face of the glacier. It can also, depending on the bathymetry, if this is kind of this enclosed little situation, it can drive a mean recirculation that then brings this warm Atlantic water into contact with the face of the glacier. So we have a lot of different things happening. We have a forced subglacial discharge plume. We have warm and salty. So both things that ice does not like. Warm and salty water coming into contact with the glacier that may melt it away. And then also as this ice itself is melting, it generates its own meltwater plume that can enhance melting. So lots of stuff happening here. Can also have big chunks of the iceberg or the glacier ultimately fall off when it is unstable enough. So we're trying to boil this down again to turbulence for today because I'm a fairly new professor and we're trying to think of what are the easiest ways to start all of these really complicated problems. So what we've done, have another turbulence tank, this little guy that has 20 jets that are in all of the corners and edges facing towards the center. And we want to create turbulence, put a sphere of ice in the middle of that, and see how the water temperature, how the turbulence kinetic energy and other statistics, and the salinity can possibly cause the ice to melt faster than it would if it were just sitting in just that salt and whatever temperature water alone. And so basically, what do I have? And the other question is it possible to melt ice at 0 degrees Celsius? We talk about dissipation, well, and with no salinity, because the salt water would melt it, but we talk about dissipation as generating heat, all right? But how much heat? Is it actually something that you can feel? So I don't have the answer to that today, but it is one of the things that's kind of on my list. So I'm gonna go back one. Well, here's how the tank works, so you can. Oh shit, this should be a video. If not, that's okay. Okay, so this shows bubbles. Usually you wouldn't have the bubbles in here, but we left air in the tank just so you can kind of get a sense for that random algorithm again. So these jets turning on and off to create a core of turbulence. The idea with the ice going in here is if you have ice sitting in a cup of hot water, ice sitting in a cup of cold water, it's going to melt fast in the hot water. But if you stir the cold water, the ice has a meltwater, like little, I'll say, plume or layer coming off of it, insulating it from the rest of the water around it. If you keep stirring away that meltwater that's insulating it, and even if the water beyond that isn't really hot, but it's still warmer than the meltwater was, but you're constantly replenishing that. That's kind of how the turbulence is going to enhance that ice melting rate. Okay, so this is our goal. So this is how the turbulence is enhancing the melting. To measure this, we have fluorescent ice spheres. This is a little thing that we thought it was little. It took my student, I think, 4 months to figure out how to uniformly dye fluorescent ice. She bought a lot of things off of Amazon and everywhere, talked to some companies, and what we ended up doing was realizing popsicles are pretty easy to make. And so we put a little bit of sugar in it, so we cheated. But it makes these really beautiful fluorescent ice spheres. We will deal with the sugar in terms of all of our dynamics, don't worry. But we have a little bit of sugar that makes this possible. So if we put the ice sphere into the tank and turn on the laser, as melting occurs, and the lighting on this is going to be variable. So sorry, we were just kind of messing with it, and it bounces around, but this is what we got for the videos today. As the ice melts, you'll see all of these little, tiny plumes coming off, wisping away off of this thing. And that's why we need it to be fluorescent, so that we can use, again, LIF, that laser-induced fluorescence, to try to quantify the instantaneous melting that's coming off of this. We can also quantify the bulk melting just by the diameter of the sphere, assuming that it stays spherical. This does not exist in nature. There are not these wonderful little ice spheres in isotropic turbulence, but this is just one piece of a very, very large puzzle, where it seems that all of the recent field literature says that glaciers are melting about 10 times faster than our models predict, and the models don't have a great way to incorporate the fluid dynamics, and specifically the turbulence transfer coefficients. So that's why we're starting super fundamental here. The goal is to ultimately make ice sheets that go into the big turbulence tank, start to increase the stratification and kind of those other pieces that we've talked about today to build this up into an experimental program that complements what is actually happening in the field. So we just can measure the diameter. It melts faster when you have higher turbulence, as you can imagine. And I think I already said all this anyway. I'll show you a few pictures of our lab, and then I'll entertain many questions, hopefully. This is our lab. This is before we actually had the turbulence tanks in it. So right now this has the two main turbulence tanks in it. These are my original grad students who have since graduated. This is what I will be spending my weekend on when I get back to Austin. We're renovating a lot of old stuff. This is a flume from 1972. When I got there, I had a steel bottom, really, really nasty glass walls that were cracked and cloudy and a mess. It had gutters on this because it leaked so much water that it just rained, not on purpose. So I ripped everything out as much as I could, and we're putting acrylic and glass back in here to turn this into a nice recirculating flume. It tilts I'm going to put in a wave maker so we can have waves and or current in here. We also have a big outdoor flume that we do a lot of Department of Transportation projects in, but it also has a lift gate. So we have proposals to do like tsunami research and some tsunami like interacting with sand dunes. It's a huge facility, but it works for what we need it to. It's also outside, so we could, you know, grow natural vegetation, maybe put some creatures in there. In addition to the tadpoles that sometimes come through. And there is a creek adjacent to campus. It's extremely polluted. The civil engineering building's sewage line used to, by accident, drain directly into this creek. That was actually the cleanest that the creek ever was, because at least it gave it a constant flow. And then when they redirected the pipe, it got even worse. So you can imagine what's in here. I'm going to study it, because why not? But it's gross. And so this is and a huge, basically, acknowledgement to my awesome students. This is my current group of students. We've shrunk, but we're 3 PhD students, 1 master's student who is going to graduate next week. But we were in the flume last week, clearing out the last bits to prepare for actual installation of acrylic and glass. So all of this work that you've seen today is due to them. This is RFA. She's our stratified expert. Aubrey on the ice, and Chen on the stand. And James has some different stuff that has to be done with plumes and median barriers. So that is the overview of my lab. And yeah, thank you. Sorry.